Welcome to Understand the Math. In this video, I'm going to walk you through exam questions on linear transformations. I'll summarize the steps needed to solve each question and carefully work through every detail so that you'll feel confident tackling these problems on your own. Let's get started. In this problem, we're given a 2x2 matrix A, and we're given a transformation from R2 to R2 that's defined as T of X is equal to A times X. We're asked to find the image under T of X, and we're given that X is a vector 3 minus 5. The first thing that we need to understand is what it means when they say the image under T of X. The image under T of X is just defined as T of X or A times X. So what we're going to need to do is we're going to need to find T of X, and we're going to multiply A times X. Let's go ahead and do that. Our T of X is equal to A times X. Our matrix A from above is 1, 4, 3, 6. And then we multiply this by our vector X that we're given, 3 minus 5. And we get 3 minus 15 in our first component, and then 12 minus 30 in our second component. And this gives us that T of X is equal to minus 12 minus 18. So the vector minus 12 minus 18 is the image under T of X. In this question, we're given a 2x2 matrix A and a 2x1 vector B. And we're told that T is defined by T of X is equal to A times X. And we're asked to find a vector X whose image under T is B. And then we're asked to determine whether X is unique. Let's summarize what we need to do. We need to find X from A times X is equal to B. The way that we're going to do this is we're going to create an augmented matrix, A augmented with B, and then we're going to put it in reduced echelon form so that we can find vector X. Let's go ahead and create our augmented matrix. We have 1, 2, 3, 4, and we're going to augment that with our vector B, which is 1, 7. We need to put this in reduced echelon form. So I'm going to begin by circling the pivot, and we're going to get a 0 below this pivot. So to do this, we're going to take row 2, and we're going to replace it with row 2 minus 3 times row 1. Our row 1 is going to stay the same, and then our row 2 is going to become a 0. We pick up a minus 6 plus 4 gives us a minus 2, and then we pick up a minus 3 plus 7, which gives us a 4. Now let's go ahead and we'll circle our next pivot. We need this pivot to be a 1, so we're going to take row 2 and replace it with row 2 divided by minus 2. We're just going to scale row 2. So our bottom row becomes 0, 1, minus 2, and then our top row stays the same. Let's now go ahead and circle our pivot again. And now what we need to do is we need to get a 0 above that pivot. So we're going to take row 1 and replace it with row 1 minus 2 times row 2. This gives us the matrix 0, 1, minus 2. And then our top row becomes a 1, 0. And we have a minus 2 times a minus 2 gives us a 4 plus 1. And that gives us a 5. Let's go ahead and circle our pivots. And those are the variables that we're going to be solving for. So our first variable is x1, and that's equal to 5. And then our second variable is x2, and that's equal to minus 2. So our vector x is equal to 5 minus 2. So that's our vector whose image under T is B. We have a pivot in every column, and that tells us that we have one solution, so we can conclude from that that X is unique. In this question, we're given a matrix A and a vector B, and we're told that our transformation is defined by T of X is equal to A times X. And what we're asked to determine is if B is in the range of T. I think the hardest part of this problem is trying to figure out what does that really mean. B is in the range of T if AX is equal to B has a solution. So that's what we have to determine if A times X is equal to B has a solution. So to do that, what we're going to do is we're going to take matrix A, we're going to augment it with B, and we're going to put it in echelon form. The reason for that is when we want to determine what type of solution we have to put our augmented matrix in echelon form. We don't have to put it in reduced echelon form. And then once we have our augmented matrix in echelon form, we're just going to be able to see then if a solution exists. So we're going to start by creating our augmented matrix. Our A is 1, 3, 1, minus 3, minus 5, 7. And we're going to augment that with 3, 1, 0. Let's go ahead and let's circle our pivot. And we're going to start by getting zeros below that pivot. The row operations that we're going to use is we're going to take row 2 and we're going to replace it with row 2 minus 3, row 1. And then we're going to take row 3 and we're going to replace it with row 3 minus row 1. Let's see what this gives us. Our first row stays the same. And then our second row, we're going to get a 0. We're going to pick up a 9 minus 5, which is going to give us a 4. And then we're going to have a minus 9 plus 1, which is going to give us a minus 8. And then in our third row, we're going to have a 0. We have a positive 3 plus 7 gives us a 10. And then we have a minus 3 plus 0 gives us a minus 3. Now we're going to go ahead and we're going to circle our next pivot. Notice that this would be a lot easier if this pivot were equal to 1. So we're going to do a scaling and we're going to take row 2 and replace it with row 2 divided by 4. And that'll make things a lot easier. Our first row stays the same. And then our second row, we're going to divide each term by 4. So we have 0, 1, minus 2. And then our third row stays the same. We'll circle our pivot. And now what we need to do is we need to get a 0 where that 10 is. The row operation that we're going to use is we're going to take row 3 and we're going to replace it with row 3 minus 10 times row 2. Let's see what we get. Our first two rows are going to stay the same. And now our third row is going to change. We're going to pick up a 0, and then we're going to have a minus 2 times a minus 10, which is a 20, minus 3 gives us a 17. Let's now take a look at this row right down here. In this row, what we're going to have, if we translate it back into algebra, is we're going to get a 0x1 plus 0x2 is equal to 17. And that's going to give us 0 is equal to 17, and that can't happen. So that tells us that for this problem, we have no solution. And because we have no solution, we can conclude that B is not in the range of T. In this question, we're given a matrix A and a transformation T defined by T of X is equal to A times X. The question we're asked is what is the domain and codomain of our transformation T? To answer this question, we first have to understand what the domain and the codomain is. The domain is the Euclidean space X is in. And then the codomain is the Euclidean space that B is in. In order to find out what the domain and the codomain is, what we're going to do is we're going to look at the sizes of X and B in the equation A times X is equal to B. I'm going to begin by writing down A times X is equal to B, and then we're not going to plug in matrix A. What we're going to do is just look at the size of matrix A. So matrix A has 2 rows and 3 columns, so it's written as 2 by 3. And then in order to multiply it by a vector X, this inner number has to match. So our X has to be a 3 by 1 matrix. And then we can think of these 2 numbers as canceling, and that tells us that our B then is going to be a 2 by 1 matrix. So let's write down that X is an element of R3, and B on our right-hand side is an element of R2. So let's go back up here and look at the top here. Our domain is the Euclidean space that X is in, and that's equal to R3. So we'll say that our domain is R3. And then our codomain is the Euclidean space that B is in. So our codomain is equal to R2. So the key to this problem is starting with the equation A times X is equal to B and looking at the sizes of A, X, and B. In this problem, we're given that T of x1, x2 is equal to the vector 2x1 and then 4x2 plus 3. And we're asked to determine if this transformation is a linear transformation. Let's start by understanding what a linear transformation is. T of x will be a linear transformation if T of x can be written as a matrix A times a vector X. So what we're going to do to solve this problem is we're going to check if T of X can be written as A times X. It's going to be really helpful if we start by taking our transformation and writing it as a vector. So let's go ahead and let's do that. So we have T of our vector x1, x2 is going to be equal to the vector. And before we do this, let's notice that we have 1 comma. That comma tells us that we're going to have 2 components, and it separates those 2 components. So our first component is going to be 2x1, and then our second component is going to be 4x2 plus 3. Our goal is to see if we can write this as A times X. So what we're going to do is let's pull this apart and try to write it as a matrix A times a vector X. I think an in-between step that will help is if we go ahead and write this. So let's write 2x1, and then there's no x2s, so let's write this as 0x2. And then in our second component, there are no x1s, so let's write 0x1 plus 4x2 plus 3. And that will really help us to determine what A is going to look like. So what we're going to do is we're going to create a matrix A that multiplies x1, x2. When we look back at this matrix, we can see that our A is going to be 2, 0, 0, 4. And then we have this extra component. So what we're going to do with that component is we're going to have to add on a vector 0, 3. So our transformation is a times x, but it's not just equal to a times x because we have this extra vector, which we can just call vector p. So we can say that our transformation is not equal to a times x because of this additional vector p. So because of this, our answer is going to be no, our transformation is not a linear transformation. The other thing that we could have looked at is we could have seen what t of 0 is. So if a transformation is linear, the idea is that the origin remains fixed. So t of 0 should be equal to 0. When we come up here, and if we were to plug in that x1 and x2 was equal to 0, you can see that t of 0 is equal to 0.3, and it's not equal to 0. So the idea is that the origin does not remain fixed, which means that this is not a linear transformation. In this problem, we're told that we have a transformation t from R3 to R2, and it's a linear transformation, and it's defined by t of xyz is equal to that vector, and we're asked to find the standard matrix of t. I think students often struggle with this problem because they have a hard time remembering what the standard matrix of t is. So let's walk through this. If t of x is a linear transformation, it's defined as t of x is equal to a times x, and that a is our standard matrix of t. So to solve this problem and find the standard matrix of t, what we're going to do is we're going to write t of x as a times x, and then we're going to be able to back out what matrix A is. Let's begin by writing our transformation as a vector. So we have t of xyz is equal to this vector. And notice up here that we're going to have 1 comma. So that means that we're going to have 2 components in our vector. So we'll write our vector like this. And our first component is going to be 3x plus 2y plus z. The commas just separate each component. And then the second one is going to be 5y minus z. Before we go ahead and break this down into a matrix times a vector, let's go ahead and rewrite this as 3x plus 2y plus z. And then because we have no x's in our second component, I'm going to write this as 0x plus 5y minus z. And then now we can exactly see what our matrix A is. It's going to be 3, 2, 1, 0, 5 minus 1. And this is going to multiply our vector x, y, z. What we were asked to find in this problem is the standard matrix of t. So that is matrix A. So we can write down that the standard matrix of t is this matrix right here. 3, 2, 1, 0, 5, and minus 1. In this problem, we're told that we have a transformation t from R2 to R2, and it is a linear transformation, and we're told what t of 1, 0 is, and t of 0, 1, and then we're asked to find the image of this vector 4, 3 under the transformation t. Let's try to understand what we're being asked to find. The image of any vector x under t is just a times x. Let's now remember what A is. A is our standard matrix, and A is defined as T of E1 and T of E2. let me write down what E1 and E2 are. E1, because we're in R2, is going to be a 2 by 1 vector, and it's 1, 0. And then our E2 is equal to 0, 1. And these just come from our 2 by 2 identity, 1, 0, 0, 1. E1 is the first column, and then E2 is just the second column. Notice in our problem that this is E1 and this is E2, so we were actually given what T of E1 is and T of E2 is. What we're going to do to solve this problem is we're going to find our matrix A, and then because we want to find the image of X under T, which is A times X, we're going to compute A times X. Let's start by writing down what A is. So A is our T of E1, which is this vector. So this is 3 minus 2. And then our T of E2 is that vector, and that's a 1, 4. So we have our matrix A, and now all we have to do is find the image of 4, 3 under our transformation. So we're going to take A, and we're going to multiply it by X, which is our vector 4, 3. So let's write down A, 3, 1, minus 2, 4. And we'll multiply it by vector X, which is 4, 3. And this is equal to 12 plus 3, and then a minus 8 plus 12. So our answer is going to be a vector with the first component of 15 and the second component of 4. So vector 15, 4 is the image of vector 4, 3 under our transformation. In this problem, we're given that we have a transformation T from R2 to R2, and it is a linear transformation, and we are given T of 2, 2 and T of 3, 5, and we're asked to find the transformation of 1 minus 1. This is a difficult problem because it has a couple of steps that we have to do. Let me go over our steps first, and then we'll go ahead and solve the problem. The first step that we have to do is we have to write the vector that we're given, go ahead and do that in green, 1 minus 1, as a linear combination of the two vectors that we have a transformation for. Once we do that, our second step is to just compute the transformation that we're asked to find. So let's go ahead and let's start with our first step. We're going to take our vector 1 minus 1. That's the vector that we want to find the transformation of. And we're going to write it as a linear combination of the two vectors that we know the transformation of. So this is C1, 2, 2 plus C2 times 3, 5. I always put a star by this for my students because I think this is the hardest part to remember in this problem. Once you have this, it gets a little bit easier. In order to find C1 and C2, what we're going to do is we're going to create an augmented matrix, 2, 2, 3, 5, and we're going to augment it with 1 minus 1. And what we're going to do is we're going to put this in reduced echelon form to find C1 and C2. Let's begin by circling our first pivot. And what we want to do is we want to get a 0 below that pivot. So the row operation that we're going to use is we're going to take row 2 and replace it with row 2 minus row 1. So this is going to give us the matrix. Let's see, the top row stays the same. And then the bottom row becomes 0. We have a minus 3 plus 5, which is 2. And then a minus 1, which is minus 2. We'll circle our next pivot. And we want this pivot to be equal to 1, so we'll do a scaling. And we'll say that row 2 is going to become row 2 divided by 2. And our new matrix is 2, 3, 1. And then our bottom row changes, and it becomes a 0, 1, minus 1. So we have the forward phase of our algorithm done. Now let's circle our pivot. And let's get this number to be a 0. So to do that, we're going to take row 1 and replace it with row 1 minus 3 times row 2. Our bottom row is going to stay the same. And then our top row is going to be a 2. This is going to become a 0. And then we have a minus 1 times a minus 3, which gives us a 3. We add it to that 1, and we get a 4. Hang with me. We're almost done with our reduction. Let's circle this last pivot, and that needs to become a 1. So we're going to take row 1, and we're going to replace it with row 1 divided by 2. So our top row becomes a 1, 0, 2, and our bottom row is 0, 1, minus 1. So this tells us that C1 is 2, and C2 is equal to minus 1. So what we're going to do is we're going to rewrite 1 minus 1, just like we did up here. But now we're going to plug in what C1 and C2 are. So C1 is a 2, so this is 2 times 2, 2, minus 1 times 3, 5. Now we can go ahead and go to our second step. Let's pull this back down and see what that is. Our second step is that we're going to compute the transformation of 1 minus 1. So we'll mark this as our second step. So T of 1 minus 1, if we just kind of distribute the transformation, this is going to become a 2. We can always take a constant out, times the transformation of 2, 2, minus 1 times the transformation of 3, 5. This is the next tricky part of this problem, is what we have to do is we have to remember that we were given at the beginning what these transformations are. So this becomes 2, and the transformation of 2, 2, if we go back up, got to go all the way back up. Here it is. It's equal to 1 minus 2. So let's plug that in. 1 minus 2. And then we subtract off the transformation of 3, 5. Let's go all the way back up. Where is that? That's right here, and it goes over here. So that's 2 minus 3. We'll plug that in. And then we just have to add these up. Now let's go ahead and write down what this is. Our first component, we have a 2 minus 2. And then in our second component, we have a minus 4 plus 3, which gives us an answer of 0 minus 1. So our transformation of 1 minus 1 is the vector 0 minus 1. In this problem, we're asked to find the standard matrix T from R2 to R2 that first reflects points through the vertical x-axis and then reflects points about the line y is equal to x. To begin this problem, we want to remind ourselves that the standard matrix of T is our matrix A, and it's equal to the transformation of E1 and the transformation of E2. Our E1 is 1, 0, and our E2 is 0, 1. So what we're going to do to solve this problem is we're going to start with E1 and E2, and then we're just going to see how they transform. And we're going to look at one transformation at a time. So I think it might be helpful to call this one our T1, the one that reflects points about the vertical x-axis. And then let's call this one our T2, the one that reflects points about the line y is equal to x. I went ahead and gave us a graph to start. And what we're going to do is we're going to begin with E1 and E2. So I'm going to go ahead and plot those. E1 is 1, 0. So I'm going to put that right here. And we're going to call this E1. And then E2 is 0, 1. And we're going to put that right here. Now let's look at our first transformation. We'll go back up. Our first transformation reflects points through the vertical x-axis. So we're going to be reflecting about this axis. So E1 is going to stay the same because it's already on the x-axis. So let's label this, and we'll pick a different color here. Let's label this one as T of E1. And now let's find T of E2. Oh, and let's label this as T1 of E1 because we have two transformations. So E2 is going to come down here because it's going to reflect around the x1 axis. So let's label this one as T1 of E2. Now let's look at the second transformation. The second one is we're going to reflect points about the line y is equal to x. So let's look at T1 of E1 first. If we reflect that about the line y is equal to x, it's going to come up here where E2 was. So let's label this one as T2 of E1. Now let's look at what happens to T1 of E2. When we reflect that one about the line y is equal to x, it comes over here. So we're going to label this one as T2 of E2. Our standard matrix A is our T of E1, T of E2. And remember, these are the columns of A. So we can write our standard matrix A as our first column, which is our T2 of E1. Let me go ahead and highlight that. That's this one. And that's going to be the vector 0, 1. And then we have our second one, T2 of E2. And that's going to be the vector -1, 0. So there's our standard matrix for this transformation. I want to do one more thing before we finish this problem. This problem can also be solved using matrix multiplication, and I want to go ahead and do that for you. We can say that our standard matrix A is A2 times A1, and A1 comes from the standard matrix for our first transformation, and then A2 is the standard matrix for our second transformation. Our second transformation is when we reflect vectors about the line y is equal to x. So the x and y components change. So our A2 is 0, 1, 1, 0. And then our A1 is when we reflect points about the vertical x-axis. And for that one, our x stays the same, and then our y changes, so it's 0, -1. And if you go ahead and you multiply these out, you can see that we're going to get the same thing that we did from our graphical method, 0, 1, -1, 0. So whenever you're doing linear transformations like this and finding the standard matrix, or if you remember what the standard matrices are for each of these transformations, you can do it algebraically. In this problem, we're asked to find the standard matrix of T from R2 to R2 that first rotates points 3 pi over 4 radians counterclockwise, and then stretches points horizontally by a factor of 3. Let's start by looking at what our standard matrix is. Our standard matrix A for the transformation T is T of E1 and then T of E2. E1 is 1, 0, and then E2 is 0, 1. So what we're going to do to solve this problem is we're going to start with E1 and E2 and see how they transform. I went ahead and drew a graph that we can start with. The first thing that we're going to do is we're going to write down our vectors E1 and E2. So this is vector E1, and this is vector E2. Let's go back up here and look at our first transformation. Let's call this first transformation T1, and the second transformation let's call T2. So we're going to look at T1 first. It rotates points 3 pi over 4 radians counterclockwise. So what we're going to do is we're going to take E1 and we're going to rotate it 3 pi over 4 counterclockwise. So E1 is going to look like this. And then we're going to do the same thing to E2. Let's actually label this one T of E1. And then our T of E2, we have to go 3 pi over 4 counterclockwise. So that's going to pull this vector down here. And let's label this as T1 of E2. So let's go back here, up here, and add a 1 to that one. Now we can look at our second transformation. So let's go back up and look at what that was. Our second transformation stretches points horizontally by a factor of 3. So we're going to take the horizontal component of T1 and we're going to stretch it by a factor of 3. So let's look at T1 of E1. If we stretch this, that's 1, 2, 3. The horizontal component is going to look like this. So we'll label this T2 of E1. And then we're going to do the same thing here. This is 1, 2, 3. So we're just stretching it horizontally. And this is T2 of E2. Now we can write down what the standard matrix of A is. Before we do that, let's write down what T1 of E1 is. That point, because we're at a 45-degree angle and we're in the second quadrant, is going to be minus root 2 over 2, and then root 2 over 2. And then T1 of E2, because we're in the third quadrant, is going to be minus root 2 over 2, minus root 2 over 2. Now we can compute T2 of E1. What we're going to do is just stretch the horizontal component by a factor of 3. So our x component becomes a minus 3 root 2 over 2. And our y component, the vertical one, stays the same. And then T2 of E2, we're going to stretch also by a factor of 3. So that becomes minus 3 root 2 over 2. And then a minus root 2 over 2. To create our standard matrix, we're going to take our T2 of E1 and put it in our first column. So this gives us a minus 3 root 2 over 2 and a root 2 over 2. And then we're going to take T2 and put it in our second column. And this is a minus 3 root 2 over 2 and then a minus root 2 over 2. And that's our standard matrix for our transformation. I also want to approach this problem algebraically. I always find that some students will like a graphical approach and then some other students will like a more algebraic approach. So here's how to do this algebraically. You take matrix A and it is A2 times A1, where A1 is the standard matrix for our first transformation and A2 is the standard matrix for our second transformation. So our matrix A is A2. So let's think about this. A2 is the standard matrix that stretches vectors horizontally by a factor of 3. So that matrix is 3, 0, 0, 1. And then our first matrix is our matrix that rotates points counterclockwise. So I'm not going to put in the angle to start. I'm just going to write it as theta. So this matrix is cosine theta, sine theta, minus sine theta cosine theta. Now what we can do is we can go back and we can plug in 3 pi over 4. So this is cosine 3 pi over 4 minus sine 3 pi over 4, and then sine 3 pi over 4, and then cosine 3 pi over 4. Before we go ahead and let's do the multiplication, we're going to write down what these angles are. So cosine 3 pi over 4 is a minus root 2 over 2. Sine 3 pi over 4 is a positive root 2 over 2. Minus sine 3 pi over 4, we pick up a minus root 2 over 2. And then cosine 3 pi over 4, just like in the upper left, is minus root 2 over 2. Now we can go ahead and we can multiply these matrices. We pick up a minus 3 root 2 over 2 in the upper left. In the upper right, we're going to pick up a minus 3 root 2 over 2. And then in the lower left, we have a root 2 over 2. And in the lower right, we have a minus root 2 over 2. And you can notice that these two answers are the same. Either approach is totally fine for solving this problem. In this problem, we're given a matrix A and a transformation T defined by T of X is equal to A times X. And this is a linear transformation because it's T of X is written as A times X. We're asked to determine if T is 1-to-1 and or onto. Before we go into the mechanics of what to do, let's talk a little bit about what does it mean for a transformation to be 1-to-1 and a transformation to be onto. A transformation is 1-to-1 if each T of X is the image of 1x. This just means that every T of X is unique. We can think of this as thinking as T of x1 cannot be equal to T of x2. Okay, so each transformation is the image of 1x, so we can't have two transformations that are the same. The way that we can determine this by looking at a matrix is a transformation will be 1-to-1 if every column of A has a pivot. Now let's look at a onto transformation. When we have an onto transformation, each T of X is the image of some X. This means that every T of X will have an X associated with it. This will happen when every row of A has a pivot. So when we're checking to see if T is 1-to-1, we have to look at a column of A. And if we're checking if T is onto, we have to look at a row of A. What we're going to do is we're going to take A and we're going to put it in echelon form, and then we're going to see if each column and row has a pivot. Let's begin by writing down our matrix A, 2, 1, minus 6, 3, 7, 4, and we're going to put this in echelon forms. I'm going to begin by circling our pivot. I think it would be a lot easier to start if we went ahead and scaled row 1 to get a 1 in the upper left. So I'm going to say that row 1 is row 1 divided by 2. So we're going to take row 1 and every entry is going to get divided by 2. That'll make the row reduction a lot easier. Now let's go ahead and circle that pivot again, and we're going to get a 0 below that pivot. And now we can avoid some fractions. So we're going to say that row 2 becomes row 2 minus 3 times row 1. So we have row 1 stays the same. And then row 2 is going to be a 0. And then in this entry, we're going to have a 7 minus 3 halves. So what is that? A 14 minus 3 over 2, which gives us an 11 halves. So we'll squish in 11/2. And then in this next entry, we're going to have a -9 plus 4, which gives us a 13. Good thing to do is to circle the pivots, since we're looking to see which row and which columns have pivots. Let's first look at 1-to-1. So if we're looking at a 1-to-1 transformation, every column has to have a pivot. Notice that our third column does not have a pivot. So we have to conclude that our transformation is not 1-to-1. And the reason for that is that we have a column without a pivot. Now let's look at our onto transformation. You can see that every row has a pivot, so that tells us that our transformation is onto. So we're going to say that T is onto, and our reasoning would be that every row has a pivot. I think the key to this problem is just remembering that you're going to start with your matrix A and you have to put it in echelon form and then look at the pivots in each row and each column. Be sure to check out the next review video on matrix algebra. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.